Hello and welcome to today's lesson on Rutherford Scattering, which is part of the atomic structure topic in GCSE Combined Science Physics. So in today's lesson we're going to describe how we worked out the planetary model of the atom. So if we're successful and we learn in today's lesson, we should be able to state the planetary model of the atom, state how we know the planetary model of the atom from experimentation, and describe how a model of the atom has changed over time, which links into the following part of the GCSE Combined Science specification 6.4.1.3, the development of the model of the atom, which is common content with chemistry. Now, to explain the atom and what it is made from, we've got to come up with a scientific model. Now, the scientific model is an extremely important concept in science. A scientific model is an idea or a theory which is used to explain observations and data made in experiments. So there have been many models of the atom over time, from Dalton's atomic model of the atom to Thomson's Plum pudding model of the atom, to Rutherford's planetary model of the atom, to Bohr's energy level model of the atom. Now, it's important in science that we keep continually updating our scientific model with the latest experimental data. So in the future we may make further amendments to the model of the atom. Now, the scientific method is the pathway that we use in all of science and physics to update our models and ensure their accuracy according to the experimental results that we achieve. So the scientific method is as follows. Step 1. Theorize a testable model or idea. Step 2. Gain experimental values about this model or idea. Step 3. Alter the model or idea to explain the experimental values that you've gained. And then step 4. Repeat steps 1 to 3 again and again and again. Now, this is the pathway we use to update the model of the atom, and Rutherford followed this pathway when he came up with his model of the atom. Now, the model of the atom is still being updated in the present day. So in science, our model must be able to explain the observations that we make. If a model does not follow the observations made in an experiment, we must replace it with a model that does follow the observations. This means over years of discoveries, we change our scientific models to adapt to the experimental results that we achieve. And this is what happened with the atom. Now, the first model which described the atom came from a chemist called John Dalton. So John Dalton theorized that atoms are indestructible and indivisible. They can't be divided into smaller particles, which is a good idea when we explain compounds, elements and mixtures. But in 1897, experiments found the electron, and it was found to be smaller than an atom, and it was found inside an atom. This meant we needed to amend the model of the atom to include these electrons, because scientific models have to change if the experimental results show that this model is wrong. So the new scientific model is created which can explain the experimental results. So we started off with Dalton's model, but then when J.J. Thomson discovered the electron at Cambridge University, this meant that Dalton's model of the atom was no longer acceptable because now there is something inside the atom. So J.J. Thomson believed that the atom was made of positively charged matter with negatively charged electrons scattered throughout, a bit like plums in a plum pudding or chocolate chips in a chocolate chip cookie. So we call this the plum pudding model of the atom, and this model works well for explaining the existence of the electron. So the plum pudding model was the first attempt at redefining what the atom looked like. So scientists were desperate to see if this plum pudding model was correct. So the plum pudding model is a bit like a chocolate chip muffin or a plum pudding. Now, the chocolate chip or the plums represent the electrons or the negative charge, whilst the muffin or the pudding represents the positive charge. Now remember, I've said the positive charge, not the proton. Now in this idea, the muffin, the plum pudding, the atom is still completely solid. There's no space in the atom under this model. So in the following diagram, we can see that the atom is completely solid. There is no space in the atom. But just remember, we don't refer to protons in the plum pudding model. We say that this is in fact positive charge, as shown on this diagram. So this model was used to explain the experimental observation of the electrons. And it also explained why the atom is electrically uncharged, because you've got negative electrons and positive charge which cancel each other out. So as a result, the scientific model was updated with the new observations and evidence, because a new model is always proposed if we need to explain new observations and data. So Thomson's plum pudding model is what we believe the atom was until the director of particle physics at the University of Manchester, Ernest Rutherford, came along. Now, Ernest Rutherford carried out the gold foil experiment or the Rutherford Scattering experiment in 1910 to test out out the plum pudding model of the atom. So he bombarded thin gold foil with a beam of alpha particles, and he expected it to just be like firing bullets at tissue paper, because if the positive charge was as evenly spread out in the atom like Thomson suggested, the beam should easily pass through. So Rutherford got a layer of gold foil 1 atom thick. He then got a source which emitted alpha particles. Now the positively charged alpha particles were fired from a radiation gun such as uranium. Now alpha radiation was a new discovery of science at this point. It's a type of radiation emitted from nuclei which increases the stability of the nucleus. But it's also very ionizing, which means it can ionize your DNA, which can mutate your DNA, which can lead to cancer. Now an alpha particle is just 2 protons and 2 neutrons. It's commonly called a helium nucleus. So as a result, the alpha particle has a positive charge of 2 because it's got 2 protons which are positive and 2 neutrons which are neutral. Now Rutherford placed these objects, the alpha particles and the gold atoms, in a vacuum chamber. Now this is because the alpha particles would be ionized if there was air in between the alpha particle and the gold atom, because alpha particles tend to only travel about 5 centimeters in air. So if there was no vacuum chamber, the alpha particles would not even reach the gold atom. So Rutherford then placed an alpha detector on the other side of the gold atoms, and he moved the angle of the alpha detector at different points of the experiment, fired the alpha particles at the gold foil, and measured what happened to the alpha particles after they passed through the gold foil. So Rutherford expected the fast moving alpha particles to smash straight through the plum pudding model atoms. Because the alpha particles are traveling extremely quickly, the gold atoms are considered stationary, so they'd smash straight through. He thought it would be like an artillery shell being fired through a piece of tissue paper. But what actually happened? Well, when we carried out the experiment, most of the alpha particles passed through the gold foil like expected, but they didn't smash through. They went straight through because gold atoms are predominantly empty space. So the first conclusion Rutherford made is that the atom is mostly empty space. Now a few of the alpha particles, as they passed through the gold atoms, deflected away from the atom as they passed through. Now they were deflected away from what we now call the nucleus. Now the nucleus also slightly recoils in this movement. However, this is much smaller due to a larger mass, so this is called something called the conservation of momentum. Now, why does the alpha particle deflect? Well, the alpha particle is positively charged, so that means there must be a positive charge in the atom. So the positive charge of the atom and the alpha particles repel each other. Now Rutherford called this positive charge of the atom the nucleus. So Rutherford's second conclusion was that the nucleus of the atom is positively charged. Now he later realized that the positive charge of the atom could be broken down into smaller units or particles, and Rutherford called these particles protons. Now about 1 in 10,000 of the alpha particles reflected backwards when they were fired towards the gold atoms. Now just to clarify, the alpha particles do not literally reflect, rather they repel without touching the gold atoms. Now this occurs because there's a large repulsion between the alpha particles and the nucleus, causing this backscatter. Now this would only occur if the alpha particle was to directly contact the nucleus, be going to hit dead on to the nucleus. Now it was noticed that only 1 in 10,000 of the alpha particles reflected backwards, so it indicated to us that the nucleus, the site of this positive charge, could not be very large. Now it's better to talk in terms of size of a comparison between the nuclear radius and the atomic radius. So it showed us that the nuclear radius, the radius of the nucleus, must be very small compared to the atomic radius. So if only 1 in 10,000 alpha particles reflects backwards, this tells us that the nuclear radius is 10,000 times smaller than the atomic radius. So we can abbreviate the results to the following. Most alpha particles travel through the gold atoms undeflected. A few alpha particles are slightly deflected, and a few alpha particles reflect directly backwards, which you can see in the following animations of the Rutherford Scattering experiment. Now, we can compare the results expected from Rutherford scattering compared to the Plum pudding model. So if the experimental results do not fit the old model, which they don't, then Rutherford had to come up with a new model to explain his experimental results. So Rutherford devised a new scientific model which explains the observations of the experiment. So Rutherford's scattering experiment showed us that most of the alpha particles pass straight through the gold atom. What's the reason for this? The atom is mostly empty space. Most of the alpha particles are reflected when they pass near the centre of the gold atom. So the reason for this is there must be in the centre of the atom a positively charged nucleus. Now about 1 in 10,000 alpha particles are deflected by more than 90 degrees. They move backwards because the diameter or radius of the nucleus is 10,000 times smaller than the diameter or radius of the atom. So to explain these results, the new model of the atom was proposed, where inside every atom there's a nucleus which contains the mass of the atom but contains all the positive charge of the atom, and it's extremely dense. The nucleus contains most of the mass, yet has a radius 10,000 times smaller than the atom. Now the results from the alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at the centre, there was the nucleus, and that this nucleus was charged. So this nuclear model, this planetary model, replaced the Plum pudding model. But then Niels Bohr adapted this nuclear model by suggesting that electrons orbit the nucleus at specific distances, and Bohr theoretically calculated the distances at which they should exist, and this then agreed with experimental observations later made. So this amended the nuclear model. Now, like mentioned previously, later experiments after Rutherford scattering led to the idea that the positive charge of any nucleus could be subdivided into whole numbers of smaller particles. Each particle has the same amount of positive charge, and we gave the name of these particles of positive charge the proton. And then 20 years after Rutherford scattering in 1932, the experimental work of James Chadwick showed us that as well as there being positive charge in the nucleus, there was also neutral charged objects as well, which we then call the neutrons. So this led us to the model of the atom we're familiar with today, the nuclear model. So the atom is positively charged with a positively charged nucleus in the middle. The nucleus has a very small radius compared to the atomic radius. The atom is mostly empty space. The nuclear model was amended when Chadwick discovered the neutron, and the neutron is found in the nucleus, and the electron structure was amended when Bohr deduced the electron energy level structure. So let's just clarify what the Rutherford scattering experiment is. You need a vacuum and alpha source with a long half-life and gold foil 1 atom thick, and when we carry out the experiment of firing alpha particles through gold atoms, most of the alpha particles pass straight through the gold foil because most of the atom is empty space. A few alpha particles are deflected away from the gold foil because the nucleus is positively charged, and 1 in 10,000 alpha particles undergo backscatter against gold foil because the nucleus is a condensed mass in the atom with a much smaller radius than the atom. Now, why did the scientific community accept the work of Rutherford? So why did people believe this idea? Well, the first reason is Rutherford was the director of physics at the University of Manchester, so he had a great body of work behind him in physics. Secondly, he did the experiment lots and lots of times. He repeated his experiment thousands of times and got consistent results. And finally, other experimenters around the world, when they heard about Rutherford's experiment, carried out the experiment for themselves and got the same result as Rutherford. So Rutherford's work was accepted in science and his model was used because firstly, he was a respected scientist with a large body of work, the experimental results were repeated thousands of times by the experimenter, and finally the experimental results were reproduced by other experimental groups. So what have we learnt in today's lesson? New experimental evidence may lead to a scientific model being changed or replaced. Before the discovery of the electron, atoms were thought to be tiny spheres that could not be divided. The discovery of the electron led to the Plum pudding model of the atom. The Plum pudding model of the atom suggested that the atom is a ball of positive charge with negative electrons embedded in it. The results from the alpha particle scattering experiment led to the conclusion that the mass of an atom was concentrated at the centre, in the nucleus, and that this nucleus was charged. This nuclear model replaced the Plum pudding model, and Niels Bohr adapted the nuclear model by suggesting that electrons orbit the nucleus at specific distances. And the theoretical theoretical calculations of Bohr agreed with experimental observations. Now, later experiments led to the idea that the positive charge of any nucleus could be subdivided into a whole number of smaller particles, each particle with the same amount of positive charge, which we call the proton. Now, the experimental work of James Chadwick provided evidence to show the existence of neutrons within the nucleus, which was accepted about 20 years after the nucleus had been established in Rutherford Scattering experiment. Now, you should be able to describe why new evidence from the scattering experiment led to a change in the atomic model and the difference between the plum pudding model of the atom and the nuclear model of the atom. So if we've been successful and learnt in today's lesson, we should be able to state the planetary model of the atom, state how we know the planetary model of the atom from experimentation, and describe how our model of the atom has changed over time. So thank you very much for listening to this lesson on Rutherford Scattering, which is part of the atomic structure topic in GCSE Combined Science Physics. Thank you very much for listening and have a lovely day.